In mathematics, groups and coding theory is a very important topic. So today we start with some topics from groups and coding theory. Now the first unit is integers. Now these are the points which we are covering in the first unit, that is integers. These are basic concepts. In school also we have studied set of natural numbers, set of integers. So remember what is set of integers. It is denoted by Z. So it contains the numbers 0, 1, 2, 3 and so on, minus 1, minus 2, minus 3 and so on. So Z contains 0 together with all positive integers and negative integers. Now separately we are defining here set of non-negative integers, which is n naught. As the word suggests, non-negative integers. It means we are excluding negative integers from the integer set. So the set n naught contains 0, 1, 2, 3, 4 and so on. Next, the set of positive integers, that is nothing but natural number set. It is denoted by n. So it contains the numbers 1, 2, 3, 4 and so on. Now in school also you have studied less than or equal to, greater than or equal to relation. So if you consider any two numbers, then we can relate them by using less than or equal to, greater than or equal to. So the symbol a less than or equal to b denotes that integer a is either less than b or it is equal to b. For example, see minus 5 and 3. So minus 5 is less than 3. So we can write minus 5 less than or equal to 3. Similarly, 0 less than 2. So you can write 0 less than or equal to 2. So even at least one condition is true, then you can write that less than or equal to or greater than or equal to symbol. Similar way, if I consider 3 and 3 itself, then 3 is equal to 3. So I can write 3 less than or equal to 3. So see, a less than or equal to b allows the possibility that a and b are equal or a may be less than b. Similar way, a greater than or equal to b indicates that either a is greater than b or a may be equal to b. Now, one important point about any two numbers a and b or any two integers a and b is that a less than b or a greater than b or a equal to b. Now, for every pair of integers a and b, either a is less than or equal to b or b less than or equal to a or both. And when both happens, it means a less than or equal to b, at the same time b less than or equal to a, then we can say that a equal to b. Now the important theorem is division algorithm. Before studying division algorithm, see one principle that is known as well ordering principle, in short WOP. Every non-empty set of positive integers contains the smallest number. That is, if A is subset of n and A is non-empty, then there exists x in A such that x less than or equal to A for all A belonging to A. See, every non-empty set of positive integer. It means we are considering one subset of positive integers, that is natural number set. It must be non-empty. It means it should contain at least one element. Then every such set has a smallest member, that means a least member. It means what? It means we can find some element x in that set A such that x is less than or equal to A for all A belonging to A. So that is the meaning of well ordering principle. For example, consider some finite subset of positive integers, say 2, 3, 4, 5, 6. So this is a non-empty subset of positive integers. So here we can find 2 as the smallest member because 2 is less than or equal to every element of that set, that is 2 less than or equal to 3, less than or equal to 4, like that. Similarly, if I consider a set of odd natural numbers, that is 1, 3, 5, 7 and so on. So again it is a non-empty subset of positive integers. And among all these members, 1 is the smallest member because 1 is less than or equal to all members of that set. So in this way, if I consider any non-empty subset of positive integers, means natural number set, then definitely it contains a smallest member. Now, the next is concept of divisibility. See the definition. We see a non-zero integer t is a divisor of an integer s if there is an integer u such that s equal to tu. See, always remember we can divide any integer by only non-zero integer. So, a non-zero integer t is divisor of an integer s if we are getting some integer u such that s equal to tu. And in this case, this is the notation to write t divides s. For example, 6 is a divisor of 18. Why? Because here we are getting an integer 3 such that 18 is equal to 6 into 3. Similarly, I can say that 10 is a divisor of 50 because I am getting 5 such that 50 is equal to 10 into 5. But sometimes some integer t is not divisor of s. It means we are not getting any integer u such that s is equal to tu. Then what is the notation to write t is not a divisor of s? So by using this symbol, we write t does not divide s. For example, if I consider t equal to 5 and s is equal to 13. Then in that case, I am not getting integer u such that 13 is equal to 5 into u. Now, for any integer t not equal to 0, means for any non-zero integer t, we can write 0 equal to t into 0. It means by definition t divides 0. So, we are getting here that every non-zero integer divides 0. In other words, 0 is divisible by any non-zero integer. Now, any integer s is always divisible by 4 integers plus 1, minus 1, plus s and minus s. Now, the third important remark is if t divides s and if t is different from plus or minus 1 and plus or minus s, then in that case we say that t is a proper divisor of s. Otherwise, t is called as improper divisor of s. It means for s plus or minus 1 and plus or minus s, these are always divisors. So these are improper divisors of s. And if there is any other divisor, then we say that it is a proper divisor of s. For example, for s equal to 4, plus 1, minus 1, plus 4 and minus 4, these are always divisors which are known as improper divisors. Then plus 2 minus 2, these are different from these divisors, so they are considered as proper divisors of s. So these are some important remarks. Now see theorem, properties of divisibility. So these are very simple results. Now the first is if A divides B, then A divides B into C for any integer C. It means if A is dividing any integer B, then A always divides integral multiple of B. Secondly, if A divides B and A divides C, then A divides Bx plus Cy for any integers x and y. It means if A divides B and A divides C, then A divides linear combination of B and C. Third, if A divides B and B divides C, then A divides C. That is nothing but transitivity. Now we will prove one by one. Now the first is if A divides B, then A divides BC for any integer C. Now what is given to us? A divides B. So by definition we can say that b equal to a into p for some integer p. Now what we have to prove here? A divides bc. So we must get bc equal to a into some integer according to definition. So we start with bc. Now as we got already b equal to ap, putting this here we get bc equal to ap into c. Now by associativity of integers in multiplication, this is a multiplied by bc. where p into c is an integer because p and c both are integers. So finally we got bc equal to a multiplied by some integer. So by using definition of divisibility we can write a divides bc. So if a divides b, then a divides bc for any integer c. Now see the second result. If a divides b and a divides c, then a divides bx plus cy for any integers x and y. Now again start with the given part. As a divides b and a divides c, by using definition of divisibility, we get b equal to a into p and c equal to a into q, where p and q are integers. Now we have to show that a divides bx plus cy. So again we must get bx plus cy is equal to a into some integer. Now start with bx plus cy. As we got b equal to ap and c equal to aq, putting these values here, we write bx plus cy equal to apx plus aqy. Now taking a common, that is distributive property, it is a multiplied by px plus qy. Now as p, q, x, y all are integers, px plus qy is again an integer. So finally see this statement, bx plus cy is equal to a multiplied by some integer. So by definition we can write a divides bx plus cy. So if a divides b, a divides c, then a divides bx plus cy. Now the third result is transitivity. So given is a divides b and a and b divides c. So again using the definition of divisibility we write b equal to ap and c equal to bq, where p and q are some integers. Now we have to show that a divides c. So c equal to, from this statement, bq, which is equal to ap multiplied by q. Again using the associativity property of multiplication, this is a multiplied by pq. As p and q are integers, pq is again an integer. So c equal to a multiplied by some integer. So this implies a divides c. So these are some properties about divisibility. In last video we have seen the basic definitions. Now see what is the definition of prime integer. A prime is a positive integer greater than 1 whose only positive divisors are 1 and itself. So prime integer must be greater than 1 and it has only two types of divisors, 1 and the number itself. For example, 2, 3, 5, 7, these are prime integers. So if you consider 2, then the only positive divisors of 2 are 1 and 2 itself. And 2 is greater than 1, so 2 is a prime integer. Similarly, the only positive divisors of 3 are 1 and 3 itself, so 3 is also a prime integer. But if you consider 1, then by definition 1 is not a prime integer. Now the next definition is when we say that some integer is multiple of another integer. We say an integer s is a multiple of an integer t if there is an integer u such that s equal to t into u. So whenever we can write some integer as some integral multiple of another integer, then we can say that that integer is multiple of another integer. For example, 18 is a multiple of 6 because there is an integer 3 such that 18 is equal to 3 multiplied by 6. Similarly, you can say that 30 is a multiple of 10 because we can write 30 is equal to 10 multiplied by 3.